Hello, everyone. My name is Wei Zhang, first year PhD student study at Carnegie Mellon Robotics Institute. Today, I'm going to present one of our recent works that we developed a planning method to generate a trajectory which satisfies the contact-rich task constraints and avoid collisions in confined environment. And I greatly appreciate the ARM Institute to support this research work. In recent years, the intelligent robot arm has been playing increasingly important roles in both the industry and people's daily life. However, one of the biggest challenges towards the wide adoption of the robot arm still lies on the real-time motion planning, like how to enable the robot to compute the trajectory to achieve this goal in real time. Since we need to satisfy the multiple task constraints such as collision avoidance and contact maintenance, which makes the motion planning problem difficult to solve in real time. Here is a demonstration video of the application of our proposed algorithm in real-world polishing tasks. In the video, the robot is conducting a wheel-bead removing task, where the trajectory guarantees the robot is collision-free and its effector is following the wheel-bead. However, the task constraints motion planning is not a trivial task, since the task constraints can be divided into two categories. The first is the workspace inequality constraints, such as the robot should not collide with itself or with the environment obstacles. Secondly, the task inequality constraints. For example, the grinding task, the robot needs to maintain contact with the surface being dry. And there are some existing works to address the task constraints motion planning. Traditionally, researchers locally optimize the configuration in null space, such as the energy-based function. And this method often suffers from the dialog and the stability issue, and is easy to be stuck at local optima. And later on, the global planning is widely studied. And one category is sampling-based method. They're good at finding a collision-free path. However, they're often not smooth and requires a lot of sampling time. And it is hard for the random sampling to satisfy the equality constraint. On the contrary, the trajectory from the optimization-based method is often smooth and computationally efficient. However, the question still remains then, how can we incorporate the domain knowledge to efficiently handle the nonlinear equality and inequality constraint? And here we formulate the problem that we denote the robot state using X, and N is the degrees of freedom. And the robot trajectory is defined to be the sequence of the states from time 1 to time t. And the workspace inequality constraints are defined such that the robot should be collision-free with the surrounding obstacle, where D is the distance function. And the contact-rich task equality constraints are defined such that the robot body should in contact with the specific targets. And here gamma is the forward kinematics function to map the robot's configuration to the robot body part location. In our paper, we propose the generation of the contact-rich reference trajectory state by state. And therefore, the objective is specified to minimize the state evolution norm difference with respect to the equality and the inequality constraints, as well as the joint limits. In order to efficiently deal with the task constraints, here we introduce our proposed method. Firstly, the equality constraint. The challenge here is that the task constraints are highly nonlinear and are expensive to resolve. To speed up the computation, we propose to iteratively consider the first order approximation of the nonlinear equality constraint until the solution converges. And here C0 is the initial body location with state X0. And the target is to find the state X1 whose body is located at C1. Then by applying the first order linearization approximation, we have the following equation. Noting the derivative of the Fourier kinematics function as Jacobian, we can have the equation on the right, which is exactly a linear equality constraint. Secondly, to deal with the nonlinear and non-convex inequality constraints, we leverage our previous work called convex stable set, which applies iterative convexification of the inequality constraint and compute the convex stable set around the reference point as new constraints. An illustration of the convex stable set algorithm is shown in the red triangle in the right figure. And we denote the original inequality constraints are intersections of the set of semi-convex inequality constraints, which is phi x. And the convex stable set for each phi x can be found using the second equation. And more details regarding ZS can be found in the paper listed in the bottom. Here we propose the components for ICOP. And the ICOP algorithm is an incremental method which solves the desired trajectory state by state. And the main inputs for the ICOP algorithm contains the previous reference robot state and the corresponding body point in Cartesian space, and the next desired body point location. Then we apply the convex stable set to deal with the inequality constraints and linearization to deal with the equality constraint. Combine and the linearized and convexified equality and inequality constraints, the original objective function can be written into this form. The main procedure for ICOP is summarized into this figure, and at each time step, we get the next desired condition position and a contribution from the last time step. And then we enter the safe-track inner loop procedure, which iteratively formulate the convex optimization to solve for the next configuration. The inner loop stop condition will be satisfied once the next desired condition position is reached and the robot is collision-free. Next, we present our experimental design. So in our experiment, we perform trajectory planning on a wheel grinding task using the 6 degrees of freedom robot manipulator. The experiment setup is shown in the bottom right figure, where the robot is required to navigate into the silver workpiece to remove the wheel inside. And therefore, the inequality constraints require the robot should be collision-free with the workpiece, and the equality constraints require the effector of the robot should follow the detected workpiece. We also built a simulation environment as shown in the bottom left figure, which aims to mimic the real-world polishing experimental setup. Note that the real-world robot links and the workpiece have complex shapes. To reduce the computational complexity in simulation, we use a simplified geometry representations for both the robot links and the workpiece. In particular, we use the 6 capsules to wrap the robot links as shown in the left part of the figure, and we use the 6 limited area planes that intersect with each other to construct the polishing tunnel representing the workpiece. And therefore, mathematically, the prescribed task constraint can be written into this form, where at time step t, the ineffector t position computed from the forward kinematics with respect to the giant vibration, xt should collide with the next desired ineffector t position. At the same time, the closest distance between the workpiece and robot capsules and configuration xt should also be greater than 0. To demonstrate the effectiveness of our proposed method in motion planning, given different targets and obstacle configurations, we evaluate the proposed algorithm on a collection of 4 different scenarios. In those scenarios, the workpiece is mounted in different locations relative to the robot. And we consider 2 types of workpiece mounting parameters: translation along the x-axis of the work frame and rotation along the y-axis of the work frame. The 4 different mountings are illustrated in the right figure. To verify our algorithm, we compare it with the state-of-the-art nonlinear optimization algorithm, which are interior point and SQP. Both the interior point and SQP algorithms solve the nonlinear equality and inequality constraints using the MATLAB FMINCOM function. Here, we present the comparison results across the 4 different mounting scenarios compared with the interior point and SQP. Our method takes the shortest computation time to find the feasible solution, which is generally 4 to 7 times faster than the interior point and 2 times faster than the SQP. The detailed computation time for each method is reported in our paper. And we also observed that our method has the smallest TCP distance across all 4 experiments, which demonstrate that our method can better satisfy the task equality constraint. On the contrary, the interior point cannot always satisfy the equality constraint exactly, or it will fail to find a feasible solution. And similarly, we can observe that SQP fails to satisfy the equality constraint across all 4 experiments. Furthermore, we can observe that our method maintains the better average safe distance across the majority of the experiments. To demonstrate the scalability of our method in terms of the planning horizon and equality threshold, we conduct additional testing using the workpiece mounting configuration from experiment 4, and we augment the predefined ineffector trajectory using the linear interpolation and the downsample the augmented trajectory to generate cases of different planning horizons. As shown in the table, we observe that the computation time of our proposed method scales linearly with respect to the planning horizon. And we also observe that the computation time increases as the equality satisfies threshold decreases, which means the good equality threshold should be chosen to balance the tracking precision and computational efficiency. Here is the demonstration video of the planned trajectory in different polishing tasks, and we observe that all the constraints are satisfied perfectly. In conclusion, we propose an iterative convex optimization motion plan method that can efficiently handle the constraints in motion planning for redundant robotic systems subject to the workspace inequality constraints and task equality constraints. The proposed method can generate reference trajectory with high tracking precision and large safety distance in real time. And we also demonstrate the applicability of the proposed method in real-world industrial wheel grinding tasks. Thank you for your listening, and I'm looking forward to your questions.